let me just address one question from a student first. What's about the junction rule? Sometimes if you've learned this before, you may have a specific rule. In fact, if you want to write it properly, it's called sum over all the currents at a junction. If you sum all the currents at a junction, it should equal to 0. So that's in contrast with the loop rule, where you sum over all the potential difference along a loop. So here, these are the i's represents all the potential drops, or it could be raised, right? A battery would raise it, a resistor would drop potential along a loop. Right? So I don't bother calling the second one a proper rule, because I would just stare at a junction and look at what depends on what you call it, right? So let's say I have a battery here, and a battery that's facing the other way, and then a third battery that is facing yet another way, and then some resistors like this. So the first thing you want to know is that along a same branch, as long as it doesn't splits up, so from here to here, the current has to be the same. And I basically think of it like the traffic analogy. If the current on one side is larger than the current here, then you can see the charges, because current is the flow of charge, right? It's the amount of charge moving past a given point per unit time will start building up if there's more current here, if there's a higher current here than here, right? So along the branch, the opposite is true. If the current here is larger, that means it's moving faster here. Then what's going to happen in the middle? If the current is faster here than here, right? It's going to, you have lots of gaps. That's not a steady flow of, that's not a steady circuit. That's not a circuit that's flowing in its prime and its equilibrium. So we assume everything is flowing very steadily. So along the same branch, the current has to be the same. So let me call this I1, I1. And so along the middle branch, we'll give it another name, I2. Now, I1 comes over here, and then there's a branch. Of course, now the current can be different, because it's, again, like the traffic, cars splitting up in, let's say, a junction of a freeway or something like that. They will be different. But it depends on what direction you call the current. So let me call that I3, right? Along here is I3. Then I think if you stare at this, it's intuitive enough to just deduce the relationship out of here. The way I've drawn it here would be I1 plus I2 equals to I3, like this. So I wouldn't memorize directly, oh, the junction rule is always I1 equals to I2 plus I3, or whatever it's listed. It's basically learning how to label your diagrams and then using the correct labeling and write down that relationship. Does that answer your question? Okay, good. Yes, that's a yes from the chat. Good. And also, you can actually have this go the other way. If you label it the other way, let's say you've labeled it I2 going this way, for example. And because this a priori, you have no idea which way it will go. Let's say I put the battery this way, so it's kind of suggestive that it should go this way, but let's say I have them facing this way, for example, right? So remember, I remember the positive side as the longer, the shorter one looks like a minus sign. It's an easy trick to mnemonic to remember which way is positive, which way is negative. So current is the flow of positive charges. So you can see, okay, so I1 probably will go this way, but then I2 probably goes the other way, but you're not quite sure, because I3 would probably, the real current will probably go this way. And whether I2 goes to the left or to the right depends on which battery is stronger, right? If this is just 1 volt of battery, this is 100 volt, it's a very powerful battery, then let's say this is also 100 volt, probably the top and the bottom one would override the middle one and just push the current, even though this battery tries to get the current go this way, but these guys would win going that way, right? Right, so if you don't know, especially if that is one of the variables you need to find, so if you don't know what these voltages are, if you don't know what the EMFs are for these battery, what you do is you first just make a guess. So maybe I would guess this time go this way. Then you set up all the Kirchhoff's rule as we showed you in the last lecture, and at the end you might get a negative number. After you go through, you remember, you will, if you have 2 loops, you'll get 2 loop equations, one for each loop, and then you also have this extra relationship. And with 3 equations and 3 unknowns, you can first eliminate 1 variable, so you're down to 2 equations, 2 unknowns, and then you eliminate another one, you're down to 1 equation, 1 unknown. You solve that, and then you go backwards and solve the other one, and then the other one. So you get all the currents. You might end up with something like this. So let's say you end up with I1 equals to 5, all right? I2 equals to negative 0.2, I3 equals to 1.4. I'm just making these numbers up. Let's say this is your result. First of all, you plug back in the SI units. If you start everything with ohms and volts, all the SI base units, then everything is amps, all right? So that's the easy part. Then now you suddenly see, okay, what is this negative sign doing? It's basically telling me that my initial guess was wrong. This guy should be the real current is going the other way, even though I defined my variable to the right. Okay, so distinguish what is really going on and what is the variable. So if I define my variable as going to the flowing this way as positive, that's signified by me putting the arrow over here, then getting a negative result means what's really going on is the other way. It's just like if you analyze a particle in 3A, right? And you say the velocity, let's say it's in one dimension, so I just use Vx, is going this way, right? And then you do your calculation, and then at the end you realize it's -5. What does that mean? First, you'll put in your SI units or put in whatever correct units you carry forward. And then you'll think about, what does this mean? That means even though I've defined my variable going this way, it's actually in reality going the other way. Does that make sense? So no need to be afraid of, let me know in the chat. It doesn't have to be Varun or just anyone if it makes sense to you. So they'll let me know if I should keep talking or just shut up. Yeah, so the result is, the takeaway is don't be scared about getting negative sign. It just basically means how you've defined your variables. Yeah. Any feedbacks? Just let me know if it makes sense to anyone. Just stop me from keep talking, unless you want me to elaborate more. Am I still here? Just checking. Okay, good. All right. Yeah, I've actually, after last night, I actually decided to do one of the examples and record a full solution on that. So let me also upload that after today's lecture, so you can see one of the full examples. And I also address the question, if I have time at the end, maybe I'll do it live as well. But if not, then I'll upload that video so you can see how I'll solve a real problem where you might have a question, should I analyze the loop going clockwise or counterclockwise? Again, the answer is it doesn't matter as long as you get the potential rises and drops in the right direction. So you'll see it in that video. But it's also, you will also cover it in the discussion sessions, which is more focused on taking these ideas and solving them correctly. This also brings to actually a good point, an important problem solving point, which I've actually mentioned many times, but here it's particularly important as well, is define your variables that appears in your steps, in your steps or in your solution. Because especially in this topic, as you can see, what you call I2 may be different from someone who submitted their exam who defined the I2 another way. In fact, not only I2, because another person sitting next to you might actually call this I1, this I2, and this I3, right? They could have defined it this way. So if you define it this way, then in this junction, what's happening is I1 equals to I2 plus I3, right? Just looking at here. So not only are they defining them with different names, calling this one is 3, this one is 1, this one is 2, this one is 1, whatever, but also they're calling different sides positive and negative. This one says my I3 going this way, it's positive, like that. So if you write down an equation without labeling these on your diagram, even if a problem provides a diagram, that's why you should really recopy it. It takes 5 seconds to just redraw this. So don't skip out on that part, because redrawing your diagram enables you to actually define your variables. It's not really the drawing part that is the important part. It's well, that is half of it, but the other half is it gives you a chance to define your variables so that when you write down the equation, you can get partial credits. If you, let's say, yeah, I didn't really label all the, so if this is a more proper example, you label each resistor, label R, each battery label epsilon, and each branch label a current I, right? And then in your equations, you will have something like this plus 1 R1, or maybe minus I2, I'm just making this up, equals 0 like this. And then you solve, and at the end, you get these answers, for example, like this. if you don't define if you don't have I1 anywhere before your steps, let's say this diagram is void of all the labels I and R and epsilon. At the end, when you say I1 equals to 5, we cannot give you any points, even if that's one of the correct answers. Who knows, are you calculating this or this, right? So there's no way to tell unless you write it in words. That's also okay, I should say. So another way is after you got I1 and then you put a comma and then you say the current on the middle branch or on the bottom branch or on the top branch is 5 amps. All right, so that is completely acceptable. But now I let you to decide, is this easier or do you want to write out in full sentence? I'm okay with both, right? But of course, I would recommend the easier way is, just write down that and then you can just underline that and then you're done, right? The point is there must be some way to communicate to the grader or whoever's reading, even if you're not very exam-centric in the future, what we want to teach you is the general skills you can take away. It's not, we don't care if you really learn about the currents after the exam. What you take away in life is better. And one thing, part of this, the byproduct of taking away from here is you need to communicate clearly what you're really trying to say. So either you can communicate through a diagram. Let's say you're running a business, right? So you can put up a diagram and your presentations and communicate that well, or in words or in a report, as long as the things are well defined. But it's really bad if you and physics is a good training of this, because it's really bad if you have a client meeting and then you just say, oh, the number is 5 million. What is that? You need to define clearly. So physicists are very good at this. We're trained on this all our lives. So this is one skill we'd like to you to learn out of this. And also another thing is there's a disadvantage of this is, let's say you got the right answers. Let's say the bottom, and then you say middle, it's 0.5 amps. Actually, you should also say the direction. If this is going, the bottom branches of this is going to the left, the middle branch is that much going to the right. The top branch is 1.4 amps going to the left or whatever, or you can use clockwise, counterclockwise, or as long as it's clear, that's fine. If you got the correct answer, okay, so that's good. So you'll get the points in an exam. But what if you didn't get the right answer? You made a small algebra mistake, you punched in the calculator wrong or something. You made a positive and negative sign error. It's very likely. We're all human, we make mistakes. So you got this wrong. So you don't get the final grade. So you're hoping to at least get the 80% of the rest of the grade. You hope to get at least 4 out of 5, right? If you don't get the final point. The idea of these grade systems is, again, very trying to mimic real life in the sense that we all make mistakes. So we shouldn't be able, it's okay if you don't get 100% in every single problem. We all make mistakes, but if you understand your stuff, you should be able to get the other 80%. So it's forgiving in that way, that if you actually understand the stuff, it's quite forgiving that if you make an algebra mistake or make a sign error, that you can still get 80% of the points. Now, the best students, of course, you will double check your work and then you'll be very careful with all the signs. So we're awarding those, if you want to aim for another A+, then of course you can get 5 out of 5. So that's how the grades reflect, hopefully. Now, if this is a disadvantage, this kind of grading system is a disadvantage to students who don't understand what they're doing and try to just plug and chug. And in fact, we actively try to discourage that by this grade system. So hopefully that reflects that as well. So back to what I was saying about labeling is, let's say you got this wrong. How do you still get the 4 out of 5? We will try to give you as much credit as possible by looking at your steps. And if you did not label the I1, I2, and I3 with an arrow over here, and the first time we look over here is just I1, I2, there's no way we know if you have constructed your loop equation correctly, if you know what you're doing. Maybe you have, everything is correct, and the only mistake you've made is you've put a positive sign there. So maybe we'll deduct 0.5 or deduct 1 point instead of yeah, so we know exactly, oh, that's a small mistake. Okay, we'll deduct whatever appropriate points that is from there. But if you don't have anything, if you get the right answer, we'll probably assume you know what you're doing, and we'll probably, grading, we try to tweak very quickly as well. If you got the right answer, maybe we'll just give you the points. But if you don't get the right answer, and then there's no, on top of that, there's no way to tell if you understand it or not from looking at a diagram, then you'll get very, very little points. Maybe 1 point for sympathy, or it looks like you may know what you're doing, but there's no way to tell kind of point, So yeah, so that's, and what's worse is if you don't even have this, and first you immediately just plug in numbers like that, 5, 3 ohms or whatever. So if the numbers are unique, and if the grader or the TA or whoever's grading it or whoever feels particularly nice on that day, yeah, they may give you the point. But that is a very big risk, because if the numbers, if you have more than one 3 ohm resistor, if you have more than one 10 volts battery, right, there's no way to know if you know the stuff or not. Then we'll assume you don't. It is your job to tell whoever's grading it that you know yourself. It's not the other way around, that they should make the guess that you do, like that. Okay, so definitely don't start with just chugging in numbers. Try to write out what you mean before you chug in numbers. Then it's okay. Then it's good. That's a good habit. And also make sure everything that you appears in here appears in the diagram as well. So these are very important ways to score as much partial credits. And just, you know, it's a good habit, basically try to learn out of this whole physics course thing. This question, do we need to label or put it in words, or just do one? Just do one is good enough. And that's what I mean by either write things in Word or have things that is traceable. The keyword basically in your head is this. Think of whoever's reading it. Are things traceable? If I see a variable here, can I trace back to what it actually means? Yeah, so put yourself in that grader's shoes of, am I telling them what they need to know? So that's a good, just a general rule of thumb thing. And how do we know which current should go clockwise or counterclockwise? So let's focus on the blue one. Let's say that's how I defined I3, right? So if I got, let's say this is actually my answer, 1.4 amps, then it means that I3 is going in in a clockwise way, right? So yeah, like that. And I2 probably you wouldn't use counterclockwise or clockwise because it's just one straight line. Again, it's just making yourself clear. Yeah, so this is in some sense a little bit of common sense. I mean, the questions are good questions because you're worried about the points, so I completely understand that. But just the idea, if you see where we're getting at, is just trying to make it clear. But you're asking good questions on how do you make it clear. So for I2, for example, I would just say either it's going left or right. Okay. Yeah. And another question is, if the current is positive, is it always in the clockwise direction? No. I think I answered that. It depends on how you define it. If I say, let's say, yeah, I could try to say, call this I3, call this I1, and call this I2. It's completely okay. Yeah. And yeah, so in this case, if you get a positive number for I3, then it means you can either say it's going to the right or it's going counterclockwise, right? So everything on this branch is I3. Sometimes it might be, if you look at the homework problems, which are up already, by the way, the full set, including what we're going to cover today about capacitors and capacitance. In your homework, they might be a little bit more specific sometimes, but I've seen some questions are more specific, some questions are less specific. So some that are more specific may ask, what is the current through each resistor? So calculate the current through every single resistor. So if you have, let's say, let me make one more here, R4. Okay. So you will need to provide 4 answers if they ask you the current through each resistor. Let me put R4 in a vertical way here. Okay. So what you will say is, for example, let's say these are actually my results for the green label. Let's say these are the results for the green label, the latest one that I drawn. Okay. So what would you say? So you would say that, so you should give 4 answers. You should give the answer, the current through, wait, I have a blank space. Okay. The current through R1, the current through R2, the current through, remember current comes with the preposition through, and potential difference or voltage comes with the preposition across, right? That's the right grammar to use. Okay. So, and then the current through R4. So where's R1? Where did I put R1 here? Okay, so I will say the current through R1, since my variable is 5, then I will say the current through R1 is 5 amps to the right. Right. You see, because it's positive 5, so that means I've labeled it correctly. My variable is reflecting what's really going on, right? And it's 5 amps going past, going through R1 to the right. Okay, R2 is 1.4. Okay, so also it is positive. That means I've labeled it correctly. So it's going to the right as well. Okay, so this would be 1.4 amps. The current through R2 is 1.4 amps to the right. The current through R3 is what I called I2, right? But if I get a negative number like negative 0.2, that means the current through here, what's really going on, it's 0.2 amps to the right. Okay, let me erase the blue one just to avoid confusion. So you would write, I'm getting 0.2 amps to the right through I3. Does that make sense? Even though I got a negative number here. Here I'm answering the question. Here I'm solving the algebra. So my algebra might result in this, but here is really your answer. Okay, so distinguish doing all the math from actually answering real life problem. That's another thing I want you to learn in physics, right? We're not machines, because this part is any machine can do this. After you set it up, you can tell the computer to do the math. But what we are, as humans, as scientists, what we want to be able to do is look at the numbers and interpret them. Okay, so finally for R4, right? So I2 is going up. My variable I2 is going up, but it's a negative sign. So what's really going on is the current is going this way. So what I will say is it's 0.2 amps going down through the R4 resistor, right? So if I read that in full sentence, it will say the current through R4 is 0.2 amps downwards. All right. Okay, so these are great questions to clarify some of the problem solving side of things. Okay, and yeah, they'll be useful. I hope the extra video I've recorded last night will be useful as well. Now put that up. I'll put that right underneath the lecture page on Canvas. So where you normally get your UJA or YouTube links, I'll just add a extra bullet point below for example solved problem that way. All right, good.